Have you ever stopped to think about the device you're probably holding right now? We're about to go on this incredible journey, starting with something you'd find on any beach, sand, and ending up inside the microscopic brain that powers, well, pretty much everything in our modern world.
So at its core, this is the big question, right? How do you take a common rock, silicon, which is really just super purified sand, and somehow teach it to perform billions of calculations every single second? It sounds like magic, but it's pure engineering. Let's dive in.
Okay, so our journey starts with silicon. It's one of the most common elements on Earth, which is super convenient. But in its pure crystalline form, it has this really unique electrical property that makes everything else possible. Think about it like this. You've got copper, which lets electricity fly through it. That's a conductor. Then you have rubber, which stops electricity cold. That's an insulator. Silicon? It's neither. It's a semiconductor, which means we can tell it when to be a conductor and when to be an insulator. We can flip its conductivity on and off like a light switch. And that ability to control the flow is the magic key to everything. So how do we get that control? Well, engineers use this process called doping. And no, not that kind. They intentionally add tiny, tiny amounts of impurities. If they add boron, they create what's called p-type silicon, which has positive charge carriers. If they add phosphorus instead, they get n-type silicon with negative charge carriers. The real genius happens when you put these two types right next to each other, because that's how we build our fundamental electronic switch. And that brings us to the absolute hero of our story, the transistor. It is the single most important building block of, well, all of modern electronics. Every single bit of information your phone or computer crunches flows through these tiny, atomic scale switches. A modern transistor, which is called a MOSFET, has three main parts. The easiest way to picture it is just like a water faucet. You've got the source, which is where the water, or in our case, the electric current, starts. You have the drain, where it wants to end up. And then, most importantly, you have the gate. That's the handle on the faucet that decides if the flow is on or off. So here's how it works. When you apply a tiny bit of voltage to that gate, it creates this electric field that opens up a channel. Suddenly, current can flow from the source to the drain, and bam, that's your on state. We call that a digital 1. Take the voltage away from the gate, the channel closes, the current stops, and you have your off state, a 0. It's that simple, a perfect binary switch. But here's where it gets absolutely mind-blowing. We're not talking about just one switch. A single microchip, the one in your smartphone, can have over 10 billion of these transistors packed inside. Each one is just a few nanometers wide. It's a scale of miniaturization that is honestly almost impossible to wrap your head around. All right, so we have billions of switches. That's great. But how do we get them to actually do anything useful? How do you go from a simple on-off switch to something that kind of resembles a thought?
The answer is by combining these transistors into little teams called logic gates. These are the simplest decision makers you can imagine. For example, an AND gate, which is just a few transistors wired together, will only turn on if both of its inputs are also on. By arranging transistors in these clever little patterns, we create the basic rules of logic.
Now, you might think you need a whole toolbox full of these different gates to build something complicated like a computer. But here's one of the most beautiful, most elegant secrets in all of digital engineering. You really don't. You only need one, the NAND gate. It's what's known as a universal or functionally complete gate. Why? Because you can build any other logic gate, the ands, the ors, the nots, just by hooking NAND gates together in different ways. For an engineer, this is a dream come true. You can perfect just one simple, reliable building block, make billions of them, and then use them to construct any digital circuit you can possibly imagine. So now let's zoom out. If a transistor is a single brick, and a logic gate is maybe a room, then the entire microchip is like a sprawling, futuristic city. And trust me, it's not a flat one. A modern chip isn't some 2D circuit board. Oh no, it's a 3-dimensional skyscraper with 50, even more, layers, all built with a precision that's almost hard to believe. It is a staggering feat of manufacturing. I love this quote because it captures it perfectly. The chip really is a 3D metropolitan infrastructure of electronic pathways. It's not just a pile of components. It's a fully integrated microscopic city built on a sliver of silicon. And just like a real city, it has different levels. The ground floor is where all the action happens. Billions of transistors, the people of our city, are built right into the silicon wafer. Then you have the middle floors, which are this dizzying maze of copper wiring. These are the streets and highways that carry all the data traffic. And way up on the top floors, you've got the global power grid delivering energy to the entire metropolis.
So what does this microscopic city actually do for you? Let's connect all this to something you probably do 100 times a day, opening an app.
The instant your finger touches that icon, the city roars to life. In just 1,000th of a second, the CPU's control unit grabs the instructions it needs. 4 milliseconds later, the chip's math unit is executing those commands, causing billions of transistors to fire in perfect, coordinated harmony. And then, in literally less time than it takes you to blink, the whole operation is done, and the app just appears on your screen. It's incredible. For decades, the name of the game was simple. Just make the transistors smaller and smaller. But we're hitting the hard physical limits of that strategy. So what's next? Well, the future isn't just about shrinking anymore. It's about building smarter and building up in 3 dimensions. So instead of flat gates on the surface, new designs like FinFETs actually rise up from the silicon like a shark's fin. This 3D shape lets the gate touch the channel on 3 sides instead of just 1, which gives it way better control and stops energy from leaking out. The next evolution, gate all around, is even cooler. It wraps the gate completely around the channel. Think of it like going from pinching a hose to wrapping your entire hand around it. It's all about getting maximum control to make transistors even faster and way more efficient. And the innovation is not slowing down, not at all. Engineers are now stacking entire chips on top of each other, creating what are called chiplets. They're designing specialized circuits just for AI, exploring how to use light instead of electricity to send data, and even building circuits inspired by the wiring of the human brain. The silicon revolution is far from over.
So from a humble grain of sand, we have managed to construct some of the most complex things humanity has ever made. These are entire cities teeming with billions of logical switches, all working together in perfect sync. The next time you pick up your phone, just take a second to appreciate that microscopic metropolis humming away in your hand. It really makes you wonder, if we've built entire cities on silicon, what on earth are we going to build next?